I already talked about the fact that a lot of series are hard to compute explicitly. One question that sounds a lot easier to ask is whether a series ends up being infinity or a finite number. We're going to spend quite a bit of time investigating this question, and it turns out that even telling whether or not a series is infinity or a finite number is typically a difficult question. And so one way of phrasing that is, when do series converge? And so a very famous example of a series that you'll end up seeing a lot and you'll want to keep it in your mind is the so-called harmonic series. And so the harmonic series is just the name for the series, the sum from n equals 1 to infinity of 1 over n. And so you can see that these terms in this series end up going to 0. And so you might think that that's an indication that this series converges. But it turns out that in the long run, this series ends up still equaling infinity, or in other words, it diverges to infinity because the numbers don't go to 0 fast enough. And so this will end up having to impact your intuition about series in the future, because the fact that the terms go to 0 is not enough to guarantee that a series converges. And so I want to spend a little bit of time looking at how we would know that this series of 1 over n ends up diverging. And so I can write out the first few terms here. So I'm going to need to write out at least 8 of them, just so that we can see a pattern here. Okay, and so the idea here is I'm going to want to make sure that I can find chunks of this series that end up being big. And so what I mean by that is I'm going to look at this first term individually. And first, the sum of this chunk is greater than or equal to 1/2. And of course, that's true just because that number is greater than or equal to 1/2. The same thing is true if I take this next term right here. That's already by itself greater than or equal to 1/2. Then, if I take the next two terms, then this is greater than or equal to 2 times 1/4. And the reason for that is that 1/3 is already bigger than 1/4. And so that means that this is already greater than or equal to 1/2. If I look at the next 4 terms here, then they're going to be greater than or equal to this 1/8, which is the smallest of them, times 4. And so that is also another 1/2. And so now you can see that if I continued this pattern and I looked at the next 8 terms, then I would end up having these 8 terms end with a plus 1/16. And so these 8 terms would end up being greater than or equal to 8 times 1/16, which again is equal to 1/2. And so at this point you might be wondering, why am I trying to find all of these 1/2s here? And the reason is because at this point we've found a strategy where you can find infinitely many 1/2s inside this series. And because this series has infinitely many 1/2s, it must diverge. And that's just because if you added up 1/2 to itself infinitely many times, of course you would get infinity. All right, so you should really try and keep this series in mind when you're checking whether or not other series converge or diverge, because this series looks like it should converge, but it doesn't. It still diverges. All right, so that'll lead us to a discussion of what's called the nth term test right here. And this is sort of just a sanity check for how you can determine whether or not a sum obviously must be equal to infinity. And so if we're looking at an infinite series from n equals 1 to infinity of a sub n, then any time that the individual terms do not go to 0, then the series must diverge. And so in other words, that's saying if you're adding up a sum of numbers and the numbers that you're adding up to themselves, the individual numbers approach something like 1/4, for example, then if you add up 1/4 plus 1/4 plus 1/4 plus 1/4 over and over and over again, of course you're going to get infinity. So anytime that this limit is not equal to 0, that's indicating that you're adding up a positive number, or whatever it is, infinitely many times, and that'll make the series diverge. On the other hand, if the limit of the individual terms is equal to 0, then we just can't conclude anything. The series might converge, or it might diverge. And we just saw an example where the individual terms were 1 over n, and so that meant that they go to 0, but the series itself still diverges. So in the case that the terms themselves go to 0, that just means that we have to do more testing in order to figure out whether or not the series converges or diverges. And so I will just mention that it is a common mistake that happens every semester in every calculus class across the US that somebody ends up using the nth term test incorrectly to evaluate a series. And so you really need to keep in mind that if the limit of the terms is equal to 0, that just gives you no information. The only time that you can conclude something with the nth term test is when the limit of the terms is not 0, and then that tells you that the series diverges. As a quick check, let's look at this example series right here of the sum of cosine of 1 over n. And here, if we take the limit as n goes to infinity of the individual terms here, then because cosine is a continuous function, this will end up being cosine of 0, because I could just move the limit inside, and that's just equal to 1. Right? And so the limit of these individual terms is not equal to 0, and so that means that by the nth term test, this series diverges. So I'll write that out. The sum of cosine of 1 over n diverges by the nth term test. Over the next few classes, we're going to find some other tests that you can use to determine whether or not a series converges or diverges.